Hello everyone, I'm Yankun from M Group. It's my pleasure to introduce our paper. Sorry. I'll introduce it in 3 sections. And in this paper, we mainly focus on the task of sequential recommendation. Sequential recommendation aims to predict the next item a user may interact with based on his or her previously interacted items. In recent years, many methods are proposed to improve the performance of the sequential recommendations, such as RNN and self-attention-based models. As depicted in the figure, these models mainly transform items into IDs, and then the IDs are transformed into embeddings and fed into neural architectures to predict the next item. I refer to these methods as ID-based models, and recently LLMs are attracting more interest, and many methods based on LLMs are proposed to solve the sequential recommendation task. And many methods simply use LLM as the recommender to recommend the next item. They mainly transform the sequential items into text format and use the LLM to output the next item's title. And for example, in this one, it's a movie it's a movie recommendation example. The next movie recommended is this movie. And this method has some advantage that they have the real-world knowledge about the items, but there are also some shortcomings. And because LLMs cannot have inadequate recommendation of sequential patterns and collaborative signals contained in item IDs. And also the important one is that LLM has long inference latency, and they cannot be deployed online and in charge of the real-time recommendation. And the ID-based methods, they can capture sequential behavior patterns, but they lack the real-world knowledge of items. So in this paper, we propose to enhance the conventional ID-based recommenders by integrating the real-world knowledge and the reasoning capabilities of LLMs. But the challenge arises from the diverse information contained in LLMs. Sometimes it can introduce noise to hurt the performances of recommendations. For example, in this example, I want the LLM to describe the features of the movie Ashes of Time. In Chinese, it's 东邪西毒. And sometimes the LLM output many diverse and professional descriptions of the movie. For example, in this, it uses a wide-angle lens and close-ups. I think these descriptions is not suitable for common people, and will introduce noise to the recommendation. And this one is a good description because it describes some common features of the movie, and is that it will attract youngers. We think that this description is very good for the recommendation. So we want to find some ways to denoise. So in this paper, we propose a method named SIGIR, enhancing sequential recommenders with augmented knowledge from aligned large language models. First, it can add word knowledge to ID-based recommenders by feeding the LLM-generated knowledge into the ID-based recommenders. Second is model agnostic. It means that it can work with most of the ID-based recommenders. Third, it solves the long latency problem of LLMs, as it can pre-generate knowledge before making recommendations. Fourth, we propose a method to accelerate the alignment training of the recommender and the LLM. Here is the overview of our method. First, there are three core components. First is the knowledge augmentation and encode component. In this component, we use a prompt template to generate a prompt and use the LLM to generate some useful text knowledge for each item. The text knowledge enriches the recommendation dataset with additional real-world knowledge. Then in the knowledge enhancement recommendation component, we use the LLM-generated text as additional features for ID-based recommenders. It means that we still use the ID-based recommender to recommend some items, but use the text generated by LLM as features. And finally, there is an alignment training component. We train the LLM and the recommender based on the feedback of the recommendation of the ID-based recommender, and in this way we can fine-tune the LLM to generate more useful text knowledge. So here's some details. In the knowledge recommendation and encoding components, we use a template to generate a prompt to instruct the LLM to generate the knowledge for the item. The template has two key features. First, it instructs the LLM to generate the feature of the movie. It means that maybe the movie is happy and it is suitable for family. And the second is the feature of the users that will like the movie. It describes the user watched the movie.Maybe in the previous example, it described the movie will instruct the user who is young and who liked the poet movie. And the text generated can be used as the additional features for the ID-based recommender. The text, then how do we use the text? There are many ways. Maybe it can be encoded with a BERT and either a small model to get embedding, or we just use the NER or other tools to generate some keywords from the generated knowledge. And the keywords can be used as features in the ID-based recommenders. Then in the alignment training component, as LLMs store a large amount of real-world knowledge, the generated knowledge sometimes introduce noise. Here is the objective function of normal sequential recommendation. And in the formula, X is an interacted item sequence, and Y is the ground truth of the next interacted item based on the history item sequence X. And here is a new formula. In this, S is the knowledge generated by LLM, and P of Y given X and S is the probability of the ID-based recommender. It means that the probability of the ground truth ground truth item Y given the historical interacted sequence X and the LLM generated knowledge S. And here is the new formula if we use S in this formula. And we did some math derivation, and the math derivation is a bit complicated, and I won't describe in details. And the conclusion is that we use this formula to fine-tune the LLM. CTR is the parameters of our LLM. It's a derivation of this objective function. This objective function with respect to the LLM's parameters, and this is the conclusion. The meaning of this conclusion is very simple. You can just focus on this part. It means that if the ID-based recommender predict the ground truth more accurate with the LLM generated as, it is tagged. If it used as predict ground truth more accurately than predict only with. Oh, the battery is only with without the generated S, and the parameters of LLM will be updated, and the LLM will be encouraged to generate the S. It means that the S make the ID-based recommender predict more accurately. So we will encourage LLM to generate the knowledge more. And if S makes the ID-based recommender recommend less accurately, we encourage the LLM to generate that S. So also here is the algorithm of the updating of LLM and the recommender. We can focus on the line 5. If we want to update the SIGIR is the parameters of the ID-based recommender. If we update the parameter of ID-based recommender, we must use X. X is the historical impacted item, and Y is the ground truth item, S is the LLM generated item. We can know that if we want to update the ID-based recommender, we must generate S before the update. So as we all know that LLM generate S, the process is very slow and time consuming. So it just slower the update of the SIGIR. In order to avoid this, we produce a synchronous generation alignment training method. The key idea is simple. We just keep two versions of the LLM and the recommender. One version is the old version of LLM, and one version is the up-to-date LLM. When we update the ID-based recommender, the S in the formula is that is generated by the old version of LLM. In this way, the old version LLM just in the sole process, it can generate S without break, and so we can have many S, and then the update of SIGIR is won't have a break. And so the training will be will be faster. And then here is the experiments. In the experiments we integrate SRAM with various ID-based sequential recommenders. And it's simple that we just use LLM, the alignment training LLM, to generate knowledge for the ID-based recommenders. And so we can use any ID-based recommender with our method, and our method will make this ID-based recommender better. And we can see in the table, and for example, the ID-based recommender SASREC, the base is the SASREC solely, and the next row is the SASREC with LLM, but the LLM is not trained. We can see that it makes SASREC better, and with trained LLM, it is the method we use. The SRAM, it can perform more better than the not trained LLM. And the red table is that we compare our method with some LLM method. We can see that it can perform the best. And here is a case. Here is an example. It's a sequential recommendation of movie task, and the top is the knowledge generated by LLM for a movie named named the Legend, A Sound of Music. And let me see. Okay. And the bottom is the movie named. The bottom is the sound. The bottom is the Legend of the Fall, and the top is the Sound of the Music. And we can see that the right side is the LLM used in our method, and the left side is the LLM without training. And we can the right text is that the text shared by Sound of Music and the Legends of the Fall. You can see that the text generated by our LLM shared more shared more text. So in this way, the ground truth, which is Legends of the Fall, will have a higher score than the LLM not trained. In this way, our LLM can generate less diverse text, but the text is more useful than the traditional LLM. So that's all. Thank you for your listening.